We also did a little trick that microscopists often use. You can put things down on the exit diaphragm of the microscope base and image it. So this is a steel pin that I put down on the field diaphragm and imaged it, and then I put a slide in, and I slid it to the point where the clot was covering over the steel pin. It shows that the iron is denser than the steel pin. So it's a nice little way of showing that we're working with metal here, and there's other clues which you'll see as we continue on here. So that's kind of a review of the work that we did in 2020. Since then, we found clots in Nanotyrannus. You're going to see Camarasaurus today, which is the specimen that was collected in Colorado with Dr. Baugh. And of course, Dimetrodon. We decided that since we're having such great success with Cretaceous bones, that we were going to jump deeper into the geologic timescale and go for the Permian. And the Lord worked it out. We were able to connect with folks who are associated with the Oklahoma Museum of Natural History, and they took us to one of their sites. It's a already published site. It's well known, and we recovered some fascinating finds, which you're going to see today. So Dimetrodon, he was a pretty big critter. You know, he's upwards of 6 feet long. I can't remember their weight, but they're probably a pretty fierce and scary animal to be around, I would imagine. They're probably not not fast moving. They're probably slow moving, but they would have been pretty nasty if you got close to them, I would imagine. So 6 to 13 feet long, upwards, here it is, 550 pounds. Literature says extinct 40 million years before the dinosaurs, so they separate these organisms by deep time. There are 30 different species described, mostly from the U.S. Now this is really interesting. They're concentrated on our continent, and in particular in Oklahoma and Texas, the Texas red beds, which are now underwater, right? So you can't dig there anymore, but they yielded quite a bit of Dimetrodon and other Permian material. But how was it concentrated here? Because the story that we're told is that this is when Pangea was present. You've heard of Pangea, right? That's where all the continents were together in one mass. And so Oklahoma had to travel 8,000 miles over that 300 million years, yet you look at these Permian bones and they're pristine. They have no flaws in them. They have no scratch marks or abrasion marks. They don't look like they've been moved at all. And you're going to see today that I'm pulling nerves out of them. You're going to see that later. So they're thought to be very old, but the more we study these specimens, we're coming to the conclusion that everything was buried together at the same time. So think about the time element. 290,000 times 1,000. Imagine if you could live 1,000 years, right? It's 290,000 times that lifespan. That's the time element that we're talking about here for these specimens. It's almost incomprehensible. Again, I mentioned Pangea, one landmass that moved 8,000 miles. The bones are pristine, but what about the concentration? For example, in Oklahoma, there are formations called the fissure fills, and most of these limb bones that we're working with now came out of the fissure fills. And they are highly concentrated injections of sand into already existing porous rock. So somehow the rock formed, it had pores in it, and the sand with these limbs in it was injected, okay, into these fills. They call them fissure fills. And that's the only place you find these things. So, I don't know. To me, it's weird that you have to go to Oklahoma, you know, one place in the entire world to find Permian bones. I can't get past that. I don't know why that happened that way. I mean, it's just difficult to explain. So we went in May of 21, and we worked with William May from the Oklahoma Museum of Natural History to a site that's been known for 17 years, actually longer than that. He corrected me on that. For decades, this has been a valuable Permian site. You saw the video previously, so here's this surface collected femur. Right on the surface, folks. Most of these bones are right on the surface. You don't have to dig for these. They're sitting on the surface. And it's a wet, sticky clay, so you almost have to peel the bone away from this hard clay that's holding on to it. So it's a very interesting site. And we're looking forward to going back. So we thin sectioned this. We sent in a piece of it for thin sectioning, and you're going to see those pictures in a minute. But these are completely permineralized. So this femur and the other specimens that we collected, the jaw, the teeth, the ribs, completely permineralized. What does that mean? All of the organics in there was exchanged for mineral, and so it's completely mineral now. But the structures have been preserved in this permineralization, as you will see. Some really beautiful ones. So here's a piece of the jaw, a big erupting tooth here. Here's a canine tooth. We actually thin sectioned the tooth also and found clots in the tooth, which is rare because there's not a big blood supply to teeth, right? When you pull a tooth, it's like one little cord, right, that you're pulling on. But we had a lot of clots in here, and you're going to see we also went back into the literature and we pointed out in our paper that's being published this week all of the clots that we saw in the literature. So we can show you some of that too. So jaw, what else? When you look at the literature and you look at the thin sections that they're producing, what do you see? The same thing that our Triceratops horn and rib and frill showed us. These are all clots, and none of them describe these. They don't even mention it. They don't even say that this is matrix or minerals that have or calcite that has infiltrated into the bone. But nothing infiltrated. That's all iron, and all you have to do is put it under a UV microscope to show it. So this is a thin section of the Camarasaurus that we collected in Colorado. I don't think we identified which bone this was, and so what we're hoping to do is to come here to Glen Rose and go through the existing Camarasaurus specimens that are here. You guys familiar with Camarasaurus? It's kind of like Diplodocus. It had a really long neck, small head, a big body, large elephant-like feet, right, and a long tail. If you go to the Utah Field House in Vernal, Utah, that museum there, they have a standing model of it there. So we did take bone away from that dig. We did not identify the bone, so we're not really sure what it is. So we're going to come back and go through the specimens here and collect identifiable bones like vertebra ribs, jaw, if we can get it, stuff like that. And we'll thin section that. So this was just a proof of concept to see if this worked. And so we'll talk about that specimen in a second. Okay, so we're back to the femur now. Oh, but I did point out here, yeah, you can see the clots. See the clots in here? Those are the clots. And we're going to image those under UV. But let's look at the femur. So this is now a bright field picture through this thin section. And you see two things. You see a lot of clotted blood, right? This is going down a canal. And then you also see this calcite. So this was supersaturated solutions of water, probably hydrothermal flows, hot flows of water, and they were squished into the bone, and then they solidified. This calcite turned into rock over time. So this is hard rock. Now this is all calcite, and everything in here that was organic was replaced except for the iron. And there it is under UV. Now I've decolorized it just to show the binary difference between the background, the calcite, and the iron that's in the clot. And these are all blood products. These are crystallized blood products. We showed some of these pictures to an ER physician, and he started naming off the different proteins that were crystallized in this. So it's still in the bone. The calcite did not push it out. Here's a combined picture of bright field coming through, which allows us to see the Haversian canal. That's the bone around. This is the classic Haversian canal. Remember that diagram of bone I showed you at the beginning? That's how this bone is made. Nice circular Haversian canal with the opening here. But look, it's full of iron. It's full of the clot. See that? Here's another Haversian canal here, and this is less congealed but still glowing. Now I've put a couple of arrows here to show what? A clear line of demarcation, showing that the iron did not leave the canal. Iron is still in the canal, so it couldn't be responsible for preserving the cells that are out here, right? And the second thing you notice with the red arrow is this deep production of the clot down the canal. Remember, these are 40 microns thin. So the distance between this and this is 40 microns, but you're seeing the clot going all the way down the canal. All right. Now we just look at it in UV, and that's just the iron. All right. So there's one example. This is femur.
What's that kind of square shape in there, in the middle?
Which square shape? In here?
Next to it.
Out here?
Nope, the other way.
In the middle.
No, inside.
Oh, in the middle. Oh, this. That's the opening. That's the opening. Yeah. You can see this in other pictures as we go along. So, in other words, the clot is adhering to the outside of the canal, and it's leaving an opening. So the light's just passing through there. Nothing's reflecting back. But it's a good observation you made, because it is crystalline. That's why you're looking at this square. The square is being formed as a result of the crystals that grew in here. See, so good observation. You want to come on a dig with us? Here's another one showing several Haversian canals. And now you're beginning to see another feature of the iron which shows it to be a metal, and that is the polishing marks. Can you see the polishing marks in the metal? They don't show up in the bone, but they show up in the metal. This is a malleable metal. So there's another confirmation that we are looking at iron, and you can really see them here. You can only see the polishing marks with reflected light. You cannot see them with transmitted light. So they are a surface feature resulting from the polishing of the section. Here's jaw. Look at this beautiful Haversian system with all these cells in the wall surrounding the canal. And the canal is completely clotted. See that? And in UV, look at the beautiful iron that shows up with the malleable polishing marks on it. This is tooth. Same thing. Again, nice polishing marks. You can see a lot of cells. Look at all the cells. How can these cells be there? It's 300 million years old, right? They shouldn't be here. This is rib. Now in rib, the vascular system is really different. It's very simple. It's very elegant. It's often oval. And so these are oval-shaped canals that go through the bone in the rib. There's the clot in bright field. Look at that. Look at how beautiful those polishing marks are. Yeah. So, like I say, this is just being published this week. So we're really excited about these results. In this case, the bone cracked. And so all of this was already clotted and formed by the time the bone cracked, and it split the metal right in half with the crack.